let's start with the properties of the graph. A graph, just like this example, okay, it's like a connected set of these what we call vertex, and these lines are called axes, okay, connected by those axes. So these boards, okay, individually are called vertex, and the line are called edge. So when we define a graph, we usually make use of capital G, and it contains a set of vertex as well as a set of edge, represented by V and E. So vertices are also called nodes or points. Edge is used to connect two different vertices. So sometimes edge are also called arcs or lines. Okay, so you have the understanding about V and E. So graphs has two types. One, when we look at the edge, one may be called directed edge. That is, it has an orientation, it has a direction. So you can see that for this type of edge, it has an arrow pointing from the source to the destination. There's another type which is called undirected edge that has no orientation, that is no direction at all. For one vertex as U or V, then they are connected by a straight line. It means that U can go to V, V and go to U. So it is about the edge. How about the graph? We also have directed or undirected. For directed graph, every edge has an orientation. For undirected graph, no oriented edges at all. That is, all edges are undirected. So the following example shows you the undirected graph. Okay, no arrows for all the edges. And the following shows you the directed graph. Each edge has the arrow. So another term for directed graph, we usually call it digraph. Digraph, okay, it's another term to show the graph have directions. So one of the example for the graphs, just like a communication network, okay, if it allows bidirectional communication for 2 points, we can have the vertex as the city and the edge as the communication links, so that we can know which two are connected, and that is they can communicate directly, or some nodes or some cities here have to be connected through other cities. That is one example. Another example is about, you learn about the maps. It has different paths. Okay, you can go through, and sometimes, okay, you can go through some points. So with different time, the time may be regarded as the weight, okay, or driving distance as the edge. And the point again will be like a city. Okay, so this one thing. And a straight map is also okay. For this time, okay, we can consider that, okay, some roads may not be bidirectional. There are some roads that allows one-way traffic only. So in this case, you can see that if it allows only one-way travel, you can use an arrow with single head. But if it allows bidirectional or two-way traffic, okay, you can use the arrow with hex for both directions. Okay, so these are examples to illustrate the usage of digraph and the unidirectional graph. So we come to the concept of complete. Complete means the idea of complete means all the nodes are fully connected. All the possible edges, okay, will be shown. Okay, these are the examples for those n equals 1, n equals 2, n equals 3, n equals 4. You can see that all the possible vertex are connected. So here, okay, for a complete undirected graph, okay, you can see that each pair of vertices are connected by edge. So each edge is of the form uv for FVU not equals v. Remember, u and v are the vertex or are nodes. So the number of such pairs in n vertex graph is n times n minus 1. And since the edge uv is the same as the edge vu, the number of edges in a complete undirected graph is halved. Therefore, that is n times n minus 1 over 2. So the total number of edges in an undirected graph, if it is completed or complete, so is n times n minus 1 over 2. How about directed graph? So the concept is quite similar. U and V for every axis for U not equals V. And the total number of such pair of n vertex is n times n minus 1. The key difference is that for directed graph, NV is not the same as the edge VU. So the number of edges in a complete directed graph is still n times n minus 1. Therefore, the number of edges for a directed graph is n times n minus 1. So it's about the concept of the complete of the graph. Then we come to another terminology, which is degree. Okay, we learn it from the idea in the tree. The vertex degree, simply speaking, is number of edges incident to vertex. For example, you can see that this 2, the vertex 2, have 2 edges connected, and 5 have 3 vertex, 3 edges connected to it, and 3 has 1. Okay, so these are the examples to show you the degree of a vertex. And you will know that the sum of vertex degree, so actually, if we know about the definition, you will see that the sum of degrees must be equal to 2e, where e is number of edges. For example, okay, in this case, you can see that this graph have 4 nodes. Okay, for 9 is 1 degree, for 8 it has 2 degree, for this 11 it has a degree of 2, for 10 it has 1. So you can see that to sum it up, okay, 1, 2, 2, 1, the total will be 6, right? Okay, then you can see that the number of edges is 1, 2, and 3. So it's half of total number of degree. And then, okay, we have another idea which is called in degree. Okay, here we just focus on the number of edges pointing into vertex. Okay, it's number of incoming edges. Okay, for example, you can see that for 2, it has 1 arrow pointing to it, so it is 1 for the in degree. And for 8, you can see that it has no arrow pointing to it, so the in degree of 8 is 0. So how about the out degree? Okay, you can consider that. Okay, it is the number of outbound edges. Okay, going out. So if you focus again to 2, so as it has 1 outgoing edge, the out degree is 1. And you can see that for 8, it has 2. So that is the out degree. So if you look at some characteristic of them, each edge contribute 1 to the in degree of some vertex and 1 to the out degree of some other vertex. Therefore, the sum of ingress must be equal to the sum of outgress. Okay, going out and going in, which as the sum must equal to E, and E is number of edges in the diagram. So that is the idea of the key terminology involved in the graphs.